Let's quickly do two examples of plotting Bode plots of transfer functions that have real poles not at the origin. The first example that we will use is T of S is equal to 1, or let's write it like this, S plus 5. So we write it into that standard form. So T of S is equal to, we divide top and bottom by 1 over 5. So let's write it in S over 5. Okay, so we don't have to do the maths because we know how the Bode plots looks for this type of transfer function. The only thing that we have to write down is, okay, we see that the break frequency is equal to 5, so we know that omega b is equal to 5. We know that a tenth of the break frequency is 0.5, and 10 times the break frequency is equal to 50, and this is all radians per second. Okay, so now we can just directly draw the Bode plots. Okay, so we know for a transfer function with a pole not at the origin, we know it breaks away from the 0 dB line at the break frequency. So we know that that is 5. We know that, okay, it's not relevant on the magnitude, so we know that the tenth of the break frequency is 0.5, and we know that 10 times the break frequency is equal to 50. Okay, so all we have to do now is draw the Bode plots. So we know that up to the break frequency, the magnitude is 0 dB, and then after the break frequency we know that the magnitude falls by negative 20 dB per decade. For the phase, we know that up to a tenth of the break frequency, the phase is 0 degrees. We know at the break frequency, the phase is negative 45 degrees. And at 10 times the break frequency, we know that the phase is negative 90 degrees. And we can connect those 2 points. And that completes the magnitude and phase plot of that transfer function, where our transfer function was 5 over s plus 5. The second example that we will do is slightly more complicated, but still quite easy to draw. And it looks like this. 1 over 1 plus s over 30 all squared. Of course, we can interpret this as 1 over 1 plus s over 30 times 1 over 1 plus s over 30. And because we're plotting in the log domain, we can plot the magnitude and phase of each of these and then just add them together to get the magnitude and phase plots of this transfer function. Okay, so all we need to do in this case, we can see that the break frequency is equal to 30 radians per second. We know that a tenth of the break frequency is 3 radians per second. And we know 10 times the break frequency is 300 radians per second. Okay, so now we can draw the magnitude and phase plots. Okay, let's draw in the break frequency. Oops, that's 30. Okay, and let's draw it on the phase plot as well. So a tenth of that is 3, and 10 times that is 300. Okay. So let's draw the first contribution. Well, we know it's 0 up to the break frequency and then falls down by negative 20 dB per decade. Okay, for the second one is exactly the same. And all we have to do to get the magnitude plot of the overall transfer function, we can add those two. Okay, so up to the break frequency, both magnitudes is 0 dB, are 0 dB. So up to the break frequency, it stays 0 dB because 0 dB plus 0 dB is 0 dB. Okay, so after the break frequency, we can evaluate it at specific frequencies. So let's evaluate it. Let's use another color. Let's evaluate it at that frequency. Okay, so these values are obviously equal. So let's call that negative V, or V. Yeah, negative V. So negative V plus negative V is 2 times negative V. So that our overall transfer function will go through that because that is just double the distance. Same with this point, and same with every other point. Okay, so we know that up to the break frequency, the magnitude is also 0. And then after the break frequency, it goes through those points. And if you go look, this gradient is negative 40 dB per decade. Okay, for the phase, well, we know for the red curve, it's 0 up to a tenth of the break frequency. We know it's negative 45. Oh, let's do it here. Negative 45 at the break frequency, and then negative 90 at 10 times the break frequency. Okay. For the blue curve as well, it's exactly the same. And then we can just add the contributions of each. Okay, up to the tenth of the break frequency, both is 0 degrees, so it just stays 0 degrees up to the break frequency. Here, both curves values is negative 45 degrees, so if we double that, it should be negative 90 degrees. At 10 times the break frequency, both is negative 90 degrees, so our new curve will go through double that, and that should be negative 180 degrees. Okay, so our phase plot for our overall transfer function will look like something like that. Okay.